After AlexNet, convolutional neural network improved the accuracy a lot more than before, especially for image classification task and objective detection task as well. So, and the modern CNN architecture, the performance is much better than AlexNet, the 2012 algorithm. So what kind of approach can improve the performance? Naturally, when you have a neural net structure, to improve the performance, you have to either increase the depth or the width. Both also fine. Increase both depth and width also fine. Okay. So usually we can improve the performance by increasing the number of neurons per each layer, or increase the depth by stacking more layers. But the problem is with the classical convolutional neural net structure like this, the input here and many different convolutional layers here, 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 and so on. This is output. Actually, we cannot improve the performance by simply stacking the convolutional layer. There are many empirical evidence. Even the training error, although you increase the number of neurons, the number of depths, you use more parameter before, your training error does not decrease, even increase after some point. So that is kind of mystery. In a sense, we already learned that usually training error decrease by increasing the number of parameters or capacity of your model. But neural network, by increasing the number of neurons, depth, we cannot observe such monotonically decreasing training error curve. I explained why this can be happen in the previous week video. When you have the deep structure and many parameters, essentially we cannot find the solution of this. We cannot minimize the loss function. Okay? The loss shape or loss function becomes very complicated. It is almost impossible to find the solution. That is the main problem, and that is why we cannot observe such monotonically decreasing training error curve, but we have this saturated and increased training loss curve. Okay, so to improve your performance, you have to increase the depth or the width. But as you increase the depth or width, it becomes difficult to train your model. Especially when you increase the depth, it becomes much more difficult to find the solution of your loss function. Okay. And one of the main reasons for the difficulty to find the solution of this optimization problem is vanishing gradient issue. In the backpropagation, you always multiply weight matrix and the diagonal matrix filled with the gradient of your activation function. Essentially, that kind of weight matrix multiplications usually generate very tiny gradient here and some constant gradient here or huge gradient here. So this imbalance scaling of your gradient makes some oscillations or some divergence of your trajectory when you learn the simple gradient descent algorithm. So to overcome this issue, we already learned that, we already discussed that there are some Adam or RMS probe and some approach there. But even with modification, we cannot expect very nice solution, especially when you stack many layers, when you have very deep structure. Okay. So to solve this issue, to overcome this issue, to escape from the oscillation or divergence because of the vanishing gradient issue and this hardness of your training, there are two very important inventions. One is laziness structure or a shortcut. The second one is batch normalization. Okay, so what is the laziness structure? Essentially, the laziness structure having some shortcut, so add some shortcut to this deep structure. This shortcut is very powerful, so this is just simple addition. In the backpropagation, this shortcut makes some path without vanishing gradient issue. Essentially, the shortcut, this residual block, makes some identity function plus some function generated by these two convolutional layer. And this identity function part always make a gradient value 1. And this identity mapping can make your gradient path from the top can reach to the bottom without change the scale a lot. So all the layer can share almost same range of gradient value, which means your loss face, the loss shape, very smooth. Your gradient to this direction, your gradient to this direction almost same. If your gradient for this direction and your gradient for this direction is not balanced or totally different, then your loss shape looks like this, and the simple gradient descent cannot go to the optimal solution but oscillate all the time or even some diverge. So that's why we cannot train very deep structure neural network because of the unbalanced behavior between top layer and the bottom layer. But the residual structure with shortcut can make your gradient share the same norm, almost same range of norm, top, middle, bottom, almost all the time. So your simple gradient descent rule can convert to some nice local minima. So we can make very nice training error, and from that we have very nice performance. Batch normalization is also very nice technique, which essentially scale your input by this. every time you estimate the mu value, the average of your input signal and the variance of your input signal. So using the average and variance, you rescale and you rebias your input signal value x so that x hat having zero mean and unit variance. Okay, because the neural network has very deep structure and correlated each other, because this is very sequential function process, the change of the bottom layers will change the statistical behavior for this input, and the change of statistical behavior of your input will change the function behavior totally different. So one conjecture, one hypothesis few years ago was because of this covariance shift, the change of statistic below layer can make a huge bottleneck for your training, and because of that we fail to training very deep structured neural network. So to address this issue, some researchers invent this batch normalization. Every time we rescale the input so that the value having zero mean and unit variance, then although the bottom layer parameter updated and bottom layer statistic updated, you can keep the same statistical behavior all the time, so you can reuse the upper layers functionals to have very nice classification accuracy. Okay, so you first make x hat from that purpose. So every time once some bottom layer parameter updated, you recalculate mu and sigma, so that every time you make sure your input having zero mean and unit variance. But if you always scale the mu and sigma using mu and sigma, essentially this also makes your learning meaningless, because all the update below will be cancelled out because of this normalization process. All the learning will be cancelled by the bias shifting and the scaling by sigma. So we usually have to keep some information using additional parameter gamma and beta, and you recalculate the y value using gamma times xf plus beta. Here gamma and beta are parameters, and you have to learn gamma and beta using gradient descent, and basically this gamma and beta can keep some information. Okay, so this is batch normalization technique, and using batch normalization technique you can train very deep structured neural network much better than before. Okay, when you implement the batch normalization, it is very important understand how to estimate mu and sigma for each iteration. Maybe you already watched the video and where the detailed process will explain. So I'll skip the details from now.